Yeah, how's it going, everybody? It's nice to meet you guys. I'm Craig.
I will give you guys, because this booklet,
Yeah, we have
I just need to fold everything.
a little comic book that explains some of the ins and outs of DNS. It's a really cool little comic from Julia Evans, and so it's supplementary material that I think you'll enjoy. So we'll get those passed out as we get them folded. I'd like to thank Professor Murdoch for having me here today. My name is Craig Youngkins. I'm a professional software engineer. After studying here at UMBC, I did 2 tech startups. The first one was a complete disaster, and I had to fire the CEO after he had embezzled a bunch of money.
Nice.
The second one went much better and was acquired by a digital communications company. After that, I went on to work at Uber, working on self-driving cars early on in the machine learning process. And now I'm at a small media company that makes websites for Magic the Gathering, the card game. Very niche, but I really enjoy my position there. I work on back-end Python software, databases, cloud infrastructure, AI. I'm doing everything. So Sana might be confusing because Sana says that I was her student 2 semesters ago. That's true. I dropped out of college to start my my first tech startup, but recently I have been taking undergrad classes again here. So I'm in a strange position at this point, but it's good. I'm going to answer any questions about my work experience, all that stuff after class. Stick around, I'd be happy to talk with you. And I have a cool blog about technical topics.
You do?
I do. cyoungkins.medium.com. So we have a lot to go through today, and I'm going to be moving pretty quickly. But if you have any questions, please interrupt me. If I'm going too fast, raise your hand and tell me. The slides and the speaking notes will be provided to you after lecture, so just focus on listening and understanding. We talked about the comic, and in addition to this comic, there's another comic about networking concepts. That one is actually included at the end of the lecture slides that will be in the PDF that you guys will get. I know my networking concepts fairly well, but I still make mistakes. If you find any, please let me know. So today we're going to talk about networking and all the ins and outs, the OG distributed system, DNS, we're going to talk about how we layer technologies together, how change happens in the world, and this one very important fact that underpins most of distributed systems. So who really cares about networking and distributed systems? Well, computers by themselves are really cool. They can do tons and tons of math very quickly, but these days a large portion of the value that comes from our computer devices comes from their networking, their interconnectedness. It's the values from data that you don't have access to, code that you don't have access to, or compute resources that you don't have access to. If you run a Google search, it's accessing terabytes and terabytes of data out of petabytes of index, and it's being spanned across thousands of computers in the course of the milliseconds that it takes to run your Google search. It's completely infeasible for Google search, even if you had the code, to run on your local device. It's just not possible. So another reason is that it's incredibly frustrating when the internet goes out, and that just speaks to the value of how important it is for these devices to be connected. Lastly, a common interview question is to ask, what happens when you go to google.com? It's a question that the interviewer can go really deep on and assess how deep the candidate's knowledge is, because you can talk for hours about what is happening in that interaction. There's so much to talk about. All right, so let's design the internet. In this lecture, we're going to go through some of the history of the internet. I usually don't like to delve into history. Talking about punch cards and stuff doesn't really matter today, but we're going to hit the points in networking because it really matters to understand why the internet is the way it is today. So we want to send messages to other computers, and we will begin with an analogy, the postal system. So all analogies break down, deviating from the thing that they're trying to explain, but we'll use this one for a short while. So the postal system, a key aspect of it is that there are addresses. Addresses that tell you how to route mail and get the messages from place to place. So let's think about that for a moment. How many addresses do we need? This is the early 1980s, and mainframes are still in the main use case. There aren't many personal computers. RAM is very expensive, so factor that in. USPS has about 170 million delivery points in the US. Okay, so that's a lot. So let's see, how many do we need? A billion? All right, I'll give it, a billion's a lot, way more. I'll give you 4 billion, okay? 4 billion addresses, and that ought to be enough for anybody. That'll be good. Okay, great. So we're going to start with designing the internet protocol, and these addresses, we will include these addresses. So these will be IP addresses. There are other addresses, like MAC addresses, and those serve different purposes and are kind of outside the scope of this lecture. Cool, and today we see that we have this concept of addressing. V4 addresses are 4 segments called octets, separated by dots. The octets, because they are 8 bits, so they go from 0 to 255. They are all numerical. V6 addresses are the newer standard, and they are much longer and hexadecimal. So you can use something like the IP-adder command to find the IP address of your local machine. And here it's pointing, this is the loopback interface, here is the primary interface, and there is the IP address, the V4 address, and below that is a V6 address. So we can run multiple processes, and we want to be able to run multiple services on the same machine, hosted on the same IP address. So the analogy here is that if there's a large harbor where ships dock, they can dock at any multiple ports. And so we will call these logical endpoints ports. They are attached to programs, and they are bound to an IP address. So they're designated using a 16-bit int, 0 to 65,000. And there are some common port numbers that have designated use that are listed here, 80 for HTTP, etc. So when you run your service, you run it on a port. Ports 0 to 1023 are considered the well-known ports, and they have services that are assigned to them. And they can only be bound by root. So you can run your service on any port that you would like, including the well-known ones, if you're root. But for the sake of everyone's sanity, you should stick to using the assigned port numbers, the standard conventions. So when a connection is made between 2 computers, there's IP addresses on both sides, and there are ports on both sides. You might use some of these common port numbers as the destination address, but you'll also get a the destination port, but you'll also get a source port. And those are usually ephemeral ports that are assigned by the operating system for your connection. So if we add in some actual content, data that we want to send to the other computer, and some header details, then we have invented the user datagram protocol, UDP packet. And here, this is what will go over the wire. UDP is very simple, and this encapsulates most everything to know about UDP. But for other transport layers, there's more to it. We'll talk about that in a moment. Up here at the top, there's the Ethernet frame, and there's other layers above this. And those layers deal with the devices, the device layer, so whether it's Ethernet, copper, fiber, the transmission between individual devices, as well as all those details with, pulses, electrical pulses, and all those details. All those details are above and aren't really going to be covered in today's lecture. We're going to be focusing on the IP layer and above. So notice that in this packet description, the IP addresses are in the IP layer, and then ports are in the UDP layer. So as you can see, we're beginning to layer technologies on top of one another so that we can build bigger and better things. So whether we're going copper, fiber, air, this might change, but these segments below that, we can all keep that the same. And we'll see that we will switch out the UDP section for an alternative, but we will keep this IP section. So the transport protocols are layered on top of the internet protocol. That's that second layer, right? This layer right here. And so the transport protocols, they might provide connections, reliability, flow control, ports, multiplexing, or none of those things. So we're going to look at two. We've already looked at UDP, and soon we'll look at TCP. Because ports are part of this layer, it's important to understand that port 53 on UDP is not the same as port 53 on TCP. Those are different ports, even though they have the same. So, as we've invented, the UDP, the user datagram protocol, it's a bare bones layer on top of IP, and it adds ports and data, and that's about it. Now, there's, in addition to what goes on the wire, which is this description over here, there's also the algorithms that we're running and how we're controlling packets. UDP is really, really dumb and simple. It's fire and forget. So since it just sends the packet and that's it, I'm done. So there's no guarantees of delivery in the lower layers. If you send a packet over IP or UDP, it is not guaranteed to get there. Packets can become lost. In addition, there's no notion of a connection. There's no setup, no state, no teardown. It's one message, boom, it's out, and we're done. There's also no packet ordering, so if you send multiple packets, then they might arrive at the destination in some arbitrary unknown order. UDP packets are also called datagrams, and you'll see that if you in the socket interface if you use the flag sockdgram. That refers to a UDP packet. So what does that look like? So we have a client and we have a server, and we send a request, and the server sends us some data in multiple packets, and one of them gets dropped. So this seems kind of silly. Like, why would we design it this way? Well, it's a really good building block, and there are applications that tolerate this some loss of data. So if you're talking on the phone and your voice cuts out for 10 milliseconds, you're not going to be able to notice. So there are applications that use UDP, and it's a great building block for building more things on top of it. So the alternative to UDP is transmission control protocol, TCP. So it's an alternative to UDP, and it has more features. Like UDP, it adds data and port numbers, but it also adds connections. So connections are established using a series of control packets, and then within that connection, it has certain properties it has the properties of being in order and uninterrupted byte stream. So connections are also closed with a series of control packets. Whenever a host sends a packet, the receiver must send an acknowledgement packet called an ACK. And if that ACK is not received before a timer expires, then the sender will resend. So I tell you my message, and if you don't say, yeah, I got it, I will wait some period of time, and then I will tell you again until you confirm that you received the message. So sequence numbers are used in the TCP header to allow the receiver to put packets in order and notice any missing packets. So by the time that your application receives the data, it's in order without any omissions. This deduplication, the reordering, and acknowledgements, these all happen in the kernel. So let's see what that looks like. Again, we have a client and server. We send a request to the server. We get an acknowledgement back, and then we get some data back as well. We send an acknowledgement for that data. The server also tries to send more data, sends data sequence number 127, but it gets lost. So we wait, the server will wait for the timeout, and then it will resend the same data packet with sequence number 127. And then this time it reaches us, and we send an acknowledgement for 127. So this seems good. Now we can send data, and we have more confidence that it will get there. And this leads some people to say that TCP is reliable. And this term is confusing. It's true that, like, compared to UDP, TCP is much more reliable, and you have fewer things to worry about. But so you don't have to worry about the duplication, missing packets, or out of order packets. That's all handled for you. But this is really important. If I unplug the network cable, TCP is not reliable. It will not work. So, and it is very important to understand that no networking is 100% reliable. And this fact is key to the design of distributed systems. So much concern in distributed systems is, how does the system behave when the network is not working? Because time and time again, issues come up where we see that the network stops working. And that can be caused by large buffers in networking devices causing very long queue times, called buffer bloat. We'll talk about that in just a moment. It can be caused by garbage collected languages, where the garbage collection system does what's called stop the world. Everything stops, and then it does the garbage collection. And if that takes a while, it can mean that messages don't get through. There's been bugs in network interface drivers where the NIC locks up when it receives certain packets. There's routing issues. There's tons of issues. Bugs are everywhere, and so no network is 100% reliable, and you need to design distributed systems to consider what happens when the network is malfunctioning. So it is normal for there to be some amount of packet loss on a network path. And this occurs when a networking device, when an intermediate networking device is saturated and a new packet comes in. So when a networking device like a switch receives a new packet, it has a small buffer in it. of RAM, where it copies it to, and then it waits for, it does whatever processing it needs to do, and it has to send it on its way. Keep in mind, these networking devices can handle, gigabits of data per second. It's a lot of data. The buffers are not that big. But this can occur where the network congestion causes the packets to get backed up. It fills the buffer, and when the buffer is filled and a new packet comes in, the only thing that it can do is drop the packet. So this in the TCP system, this causes the sender to slow down the rate of sending to modulate how fast it's sending data and reduce the throughput to match what's sustainable. So if you think about this and you're like, well, if the buffer getting full is the problem, why don't we just make the buffer bigger? And yeah, you can do that, but it has some unintended side effects. That's the strategy that many networking device companies have taken, is adding more and more buffer so that they reduce packet loss, because packet loss seems like a bad idea. So the side effect of this, though, is that it results in much longer queue times, where packets are stuck in that buffer, and it takes a long time to get through, to run through everything in the buffer. And that means that they can be higher latency. And so this is called buffer bloat. This is one of the online tests that you can do to test for buffer bloat. I'll have a link to it in my lecture slides. But what this is doing is a test when there's no network activity. It's checking a ping, and it's like, okay, it's 57 milliseconds when there's nothing going on. But if I start a concurrent download and try to ping at the same time, then my ping shoots up astronomically. And in some connections, this is more affected on upload. So if you are playing your video game and your brother decides to download a game on Steam and saturate your network connection, your ping might go up. And this is why, buffer bloat. There are some solutions that you can apply at the router level, but
yeah. So the resources of that buffer are being split, essentially, is what you're hinting at?
So when the download is going, it's filling that buffer up, and then the ping packets have to wait through the buffer. They queue through that buffer, and it just takes a while for it to get through that buffer. Okay, so we have, back to TCP, we have this bidirectional, in-order, uninterrupted byte stream. And on top of that, we're going to build HTTP, the Hypertext Transfer Protocol. This is what is used to transfer HTML, images, video, everything. So in this example, we have a printf call that is building a string that is the HTTP request. And then we have it piped into netcat. So netcat is the Swiss Army knife of networking. And what this command is doing is it's opening a TCP connection to example.com on port 80. So that's just the TCP connection. And then on that TCP connection, we're going to send a formatted string that is our HTTP request. It's just going to say get / blah, 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 some headers, specifying the host that's required at this point. And that's it. That's all it is for a basic HTTP request. And here's the response. So we get back. This is exactly what that TCP connection is sending back in response to our request. And so we have HTTP 200 OK, great, some headers, and we eventually have some HTML. So as a systems programmer, you'll interface with these transport protocols using the operating system's socket interface. So this is an example of using the sockets interface. It opens a stream socket, which corresponds to a TCP connection. You can also open a dgram socket, which is UDP. So this sets up the socket. It says this is going to the internet, even though this is actually connecting to localhost. 127.0.0.1 is an alias for the local machine. This specifies the address that you want to connect to, the destination. We do the connect. We have this message variable, and we copy it into the buffer and send it. And then we allocate a buffer and read the response. And so this does pretty much what Netcat did on the command line in the previous example, where it reads in the message, it sends the message, and just reads the response, and then we're done. So there are other kinds of sockets. I said that there's UDP, sock dgram. There's also raw sockets, which are what is used for messages like ping. And there's also like Unix domain sockets for local communication that don't go into the IP stack. So I love this quote from Dijkstra. The computing scientist's main challenge is not to get confused by the complexities of his own making. I think that's largely true, and I frequently find myself drowning in complexity. So we use abstraction, and it's the hiding of complexity of a system by providing an interface that eases its manipulation. So we provide some guarantees, we simplify the interface, and hopefully you don't have to worry about the transistors that are on the silicon. You worry about things that are at a much higher level. It's really how we build bigger and better things. So many applications use TCP and UDP without additional layers, but we have HTTP, and that is built on top of TCP, and you can see that we start to layer these technologies together. Another example is the notion of a file in a system. It sounds like you guys are doing a lot of file system work. So in the file system interface, if the file is hosted on the local file system, or if it's in RAM, or if it's on a network file system, it's all the same file API. And you can interact with it in the same ways, regardless of where it is and what the underlying system is for hosting it. And so you can see some of that layering here. So there's Wi-Fi and wired systems. That would be, and included here is the MAC layer, MAC addresses, and more of the hardware. We designed the IP layer, and we designed UDP, and we talked about TCP over here. And all these can work together. So there's something called the OSI model, and it has a little bit more strict definitions of network layers. But as we'll see, this model kind of falls apart. So let's add in HTTP here. So HTTP, the older standard that's being used today, it can go over TCP as we showed, but it can also go over TLS. TLS is the new name for SSL. So that's for a secured connection. And we say TLS is kind of like layer 5. This one's well established that this is layer 7. New standard for HTTP 3 goes over a new protocol called QUIC, which is considered a transport protocol, which would put it in layer 4, but it also builds on UDP, which is also layer 4. So we're getting a little weird. And then you put DNS in here, and DNS can go over UDP, it can go over TCP, it can go over TLS, it can go over HTTP. And so this notion of like strict layering is doesn't really suit the flexibility and the way that we've more organically grown how we're using these technologies. But we still have the notion that we build on top of lower levels. So, HTTP3, like you mainly need to be concerned about the quick protocol and how to use that. So when you use an interface like TCP, do you need to know about the details, the implementation details, or the things below it? So if you use TCP, do you need to worry about whether it's IPv4 or v6, or whether it's going over copper or fiber or air? You're probably thinking, no, not really. But I know at least one person who would kind of disagree with that. His name's Joel Spolsky. You may not recognize his name, but I'm sure you recognize his creation, Stack Overflow. So Spolsky would argue that TCP, like all non-trivial abstractions, is leaky. It means that the implementation details from lower levels creep up in different ways through the abstraction. And so he kind of argues that you have to learn to some degree about the lower levels. And that's part of the reason that you're in this class. For example, TCP retransmission means that there can be like a wide latency variation during packet loss. So your packets come in steadily, and then there's a break, and then it comes in steadily again. And it's sometimes those details come in when you're trying to use TCP. The connections can break, and it's not like this ironclad thing that's a fully reliable thing. So you can think of this as there's still details that you need to learn about that are underneath of it. You can also think of it as you need to be pretty careful about how you make specifications. I would say that TCP guarantees that if your application receives some data, then it has received the data that was earlier in the stream. So that doesn't say that it will always receive data, and it doesn't make any assertions about when it will receive data. It just is, it's a very careful specification of what TCP provides. For me. So, in the original design of the internet, each device had a globally unique IP address, and this enabled end-to-end connectivity. In our story of the internet, it's now the 90s, and this internet thing has really taken off, and we realized that we are in trouble. So we said 4 billion was a lot, and it turns out we weren't really thinking it through. At the time, mainframes, it seemed like a reasonable choice, but here we are. There's 8 billion people, and many of whom have multiple devices, and today there are 20 plus billion devices that are connected to the internet. Obviously, we don't have enough addresses for all of them. And so 2 solutions were provided, NAT and v6. And we're going to get to those explanations in a moment. We need to take a couple digressions to talk about changes that we made to support those features. First one was that we allocated special sections of IP addresses. We created private ranges that are not routable on the public internet. And that seems kind of strange initially. It's like, wait, you can't route to these? Isn't that the purpose of communicating on the internet? Yes. But we did this so that we could have multiple copies, multiple instances of these IP ranges in private networks where we have and so that they won't conflict. So we designate some of these addresses as private, meaning that they are not routable. For example, most of your homes will use this 192.168 block. And so if my home and your home and everybody's home uses this 192.168 block, then you'll find that we have many devices that are on the internet that have the exact same private IP addresses. All right. We'll explain how this works in a couple slides. The other aspect is broadcast addresses. If you send a packet to .255, then it goes to the whole network. We will use that broadcast address in just a moment. So this is where we come into the common understanding of LAN and WAN. The division or the difference is at the router. So everything inside in your home on this side of the router is LAN, local area network, and the things outside of it going towards the internet is the WAN, the wide area network. So we use private addresses over on this side, and we use public addresses on that side. So how do we get one of these addresses? For this far, we've kind of just been assuming that we have it already. And some servers are configured with static IP addresses, but more commonly, the Dynamic Host Configuration Protocol, DHCP, is what's used to get an address. So a client will send out a broadcast request, and the server, a DHCP server, which is normally running on the router, will respond and say, here's your IP address, this is what you should use. So when a new device joins a network, you come here, you join, or someone joins your Wi-Fi, that device will send out a DHCP request, and it will get a private address. And so similarly, and your router will answer for that, will give out the addresses in that case. But there's a similar operation where your router is the one asking, and it's going to the ISP and says, hey, what should my IP address be? And the server in the ISP responds and says, this is what you should be. This is your public IP address. So it's the same process. It happens on both sides of the router. And so home routers will have two IP addresses, one local, private, and one for the public. So we've said that we have like all these copies of local private addresses, and so how does that work when you send out packets from them if we have all these copies of the private address space? And the answer is network address translation, or NAT. So part of the home router's job is to do this translation. A packet will come in from your laptop, something. Let's say that you're trying to, for some reason, trying to connect to yahoo.com. It'll construct a packet where its source address is the private address. As we described, you'll get an ephemeral port number, and that'll be your source port number. That's provided by your operating system. The destination is the IP that corresponds to yahoo.com, and we're going to connect to that well-known port number 80 to fetch the web page. This packet will be constructed on your laptop, and then it will be sent to the router. The router will first allocate you a new ephemeral port on the public IP address. So it will say, okay, 6282 is free, and it puts the new ephemeral port number in this table along with its public IP address. And on this side of the table, it writes down your private IP address and your port number that was the source port. So this is the, So then it rewrites the packet. It edits the packet that you sent it, and it rewrites the source IP to be the public IP of the router, and it rewrites the source port number to be the ephemeral port number, the new one that it allocated for you. And it leaves the destination alone. And after it edits the packet, it sends it along to its next stop on the internet interface. When the packet comes back, the packet will be bound for the destination address will be the public address of the router, and the destination port will be 6282. That packet will come in, it will look at this table and say, okay, I know 6282, that matches with this row, and it will rewrite the destination address to be the 192 address. It will rewrite the destination port to be 3585, and then it will forward the packet along on the local network, and it will go to your computer. And so this is how network address translation works, and how we're able to use multiple private IP addresses behind a single public IP address.
So, like, what happens if two services want to use the same private IP address? How does this rest them?
Use the same private IP address? So when I join my home network, and my home network is totally separate from your home network, because
Like network compartmentalization.
Because those addresses are unroutable on the internet. And so all those addresses, they sit, like, if you send out a packet for 192.168 to the internet, everything's going to just drop it, because there's no way it can be routed. And so it's all those are all like little tiny networks, and it only those IP addresses only make sense within each little network.
I see.
So oftentimes, like, what we care about is not our private IP address. We care more about the public one. For example, if you're trying to host like a game server. So private addresses are never shared. They're not useful outside the local LAN. What you're really looking for is the public IP address. So if you do IP-adder or IP-config, you'll get this address, your local private IP address. In order to get your public IP address, you need to either ask the router, or you go to a resource out external that is getting some of these packets that have been rewritten with the source address, like Google. If you type into Google, what is my IP address? It'll come back and it will tell you, and it's reading what's in the packet. So today, each IPv4 address is shared with an average of 7 devices behind it. And cellular networks that do NAT in a variation called carrier grade NAT, it can be even a lot more than that. So again, NAT was created because of the IPv4 address shortage and the explosion of the internet. So NAT adoption occurred pretty quickly, mostly out of necessity, and it continues to be widespread, but it was intended to be a stopgap. This was not the plan. So lastly, while this table is usually dynamically created, you can do an operation called port forwarding, which sticks a permanent entry in here that says, I want to host my web server on port 80. So I want all the traffic that's going to port 80 on the public IP address. I want to send it to my workstation because I'm posting a website. That's what port forwarding is. So does this make sense? How the packets get rewritten based on this table? Is this making sense? Cool. So I've described how most of the internet works today with IPv4. But like I said, this mess with NAT and private addresses It wasn't part of the plan. The plan was everyone gets a uniquely routable IP address and for there to be end-to-end connectivity. So the other mitigation that was developed was IPv6. So IPv6 was published in '98, that's 25 years ago. Whereas V4 has 4 billion addresses, V6 has a zillion. 128 bits of address space, so a lot more. So the primary goal of V6 was to prevent address exhaustion. And at a first approximation of it, while there are some there's a few more changes, there's a few more things they added onto it. Like a first approximation of it is just V4 with bigger addresses, okay? It was designed to be a largely invisible change. But this created a situation in which there was little motivation for people to adopt V6. It's not really faster, it's not lower cost, it doesn't generate revenue, and so adoption has been really, really slow. So we'll get back to V6 in just a moment, but we're going to take a little detour to keyboard layouts. So sitting in front of many of you is probably a keyboard that looks much like this one, the QWERTY layout. If you learn to type properly, you rest your hands on the home row, and where it is central to all the keys. Now, the most common letter in the English alphabet is E. Where should we put that letter? On the top row. Okay. Not one of the keys that we're usually resting our hands on. Okay, what about next? T. T is the next most common. Okay, also at the top. And then we have the vowels. Okay. This layout is far from optimal. And there are better layouts that have the potential for faster typing speed and reduced repetitive strain injury. And yet, almost no one uses them. Why?
You put that in front of me, I will never know how to type ever again.
Exactly. When you learn to type, you probably just got this keyboard. It's what everyone types on. It's got the letters written on it. Now, you've heard this now, that there are better layouts, and you're like, okay, as an individual, you could try to, even though you've been using QWERTY for many years now, you could try to learn a new layout. It will take you months, as it did me, and you'll have to deal with all the wrong keys printed on the keyboard, and you'll have this high barrier of switching on any new computer, and you have to swap the layout, and it's a high barrier. It's a high barrier. And so what we see is that in everyday use, for most everyone, the alternative keyboard layouts don't have they don't have enough benefits in order to outweigh the deep entrenchment and inertia that QWERTY has. We've settled into a suboptimal solution. There is some deep wisdom here about how change happens. If you do a startup and your product is 20% better than the current best, but the main competitor is deeply entrenched, you are unlikely to succeed with your better product. We've seen this many times with social networks. Google Plus came out trying to dethrone Facebook, failed. Unless you are Microsoft and you can push your search engine through the default in your operating system, good luck challenging Google, even if it's better. Google is in the common lexicon. So these are important things to understand. Thank you. And similarly, understanding the motivations and behaviors of individuals is key to understanding the adoption of systems and standards. So you get the individual choice of should I stick with QWERTY or should I try something new? And most of you are going to stick with QWERTY, and that's fine. But understanding how that choice at an individual level affects the whole is important. And so bringing it back to v6, well, why would we put in application support of v6 if no host had v6 networking on it? Why would we add host networking on v6 if no ISP was providing v6 addresses? Why would the ISP add v6 addresses or support v6 if no host and no applications were using it? And so v6 has been very slow to be adopted. And part of the issue was that if it's just v4 with more addresses, that's not enough to get people to do this change. If we had instead changed more aspects of v6 to improve it in some way, then there might have been a better chance of it being adopted. And the way that we have right now with NAT, it works well enough. And so we see this slow uptake of v6. So the US governing body for addresses, AARN, it ran out of v4 addresses in 2015. And you might have heard that, and it's like, well, what does that actually mean? It means that organizations can no longer get new addresses from the allocating body. But you can still use v4 addresses. You can get them for your servers through services like AWS or DigitalOcean. You can get addresses. You can also still buy addresses on the private market. They're about $35 each, bundle of 256, 9K total, easy. So it's not like it's impossible to get a v4 address. So this is kind of where we're at right now in terms of v6 adoption. So we're at about 40% of internet traffic is on v6. It's been a very long road getting here. We don't know whether this will curve upward and be exponential with momentum, or if it would be asymptotic because of a few lagging people dragging their feet, or somewhere in the middle. We don't really know. So it's kind of valid to ask, okay, if we have way more devices than addresses, and yet everything is kind of still working, like, do we really need v6, or are we good with what we have? Right now we're kind of in the worst of both worlds because we have partially deployed v6, and we're operating in what's called a dual stack environment where we're running both v4 and v6, and it just makes everything difficult. Right now we don't have the end-to-end connectivity that was part of the original design of the internet, and so we do have some limitations. When we do peer-to-peer traffic, so video conferencing, file sharing, stuff like that, like, it requires this complicated dance to get through the NAT. And in some cases, it requires bouncing traffic off of a central server because we can't get the clients to communicate directly. On carrier-grade NAT, the situation is a little bit worse because you frequently cannot forward ports, so you can't host your server. Again, carrier-grade NAT is what's used in a lot of mobile networks. And because on carrier-grade NAT, you are behind a shared public IP address with other users of the mobile network, it's not just with your house. You can, in some cases, like if there are malware or other people, it's usually somebody with malware or virus. So they go and their computer is doing nasty things. It's like sending out a bunch of packets, it's doing web scraping, something like that. And that's coming from the same public IP address as my grandma with her iPad. And so she would get a lot of CAPTCHAs. And the issue here is that it's difficult to distinguish between my grandma's iPad and this virus-laden computer because they're both going through the same carrier-grade NAT and they're both getting the same public IP address. That packet that goes to Google or wherever they get the same public IP address. So it can be really hard to tell. So lastly, v4 costs are starting to actually get pushed down onto the users of the addresses. So AWS now charges $366 per month per address. And that doesn't sound like a lot, especially for business, but it does add up when you have to use like 3 addresses per load balancer because it's in different zones, and you have many load balancers for a service, and if you have many services, it adds up. It adds up. So supporting v6 is not that complicated. It's pretty much a matter of enabling v6 on your service. For most load balancers, this is just like a checkbox in AWS. So you check the box, it allows it to operate in dual stack, and then the other component is adding a quad A DNS record. And that's it. It's honestly not that complicated, and you could be part of the change when you start working. Okay, any questions about networking? Cool.
Are you I do not?
Nope.
I was going to say, no, I'd just like to ask my question, but
Okay. No, wait, I'm going to try to do a speed run of DNS. So we'll see how far we get. So DNS is the domain name system. The primary function of it is to resolve a domain name into an IP address. So nobody likes to remember IP addresses. That would be like numbers. That would be pretty terrible. So we have the system to translate google.com into 1972 blah, blah, blah. So that's the function. I think DNS is really cool, and I've written a number of blog posts about it. It's old, it's foundational to the internet. It's like this huge distributed key value store. And it's one of the largest distributed systems in terms of like span across organizations. It's super reliable and redundant, even though things do go wrong. So what happens when you are trying to resolve a domain name? You have your browser, and your browser has a cache, and it's going to make a function call to the operating system. It's usually get adder info on Linux systems. Your operating system might have a cache, but if it fails the cache, it's going to go passed on to what's called a resolver. And the resolver is kind of the person, I like this magnifying glass because they're going to go search for it, and they know how to contact the authoritative name servers, which is where the records are, the source of truth for the records are. And so the resolver will probably need to communicate with the authoritative name servers. Those are the ones where the source of truth for what the answers to your DNS queries are. And this comment is by Julia Evans, and some of this is in your paper that you have there. But so there's a distinction between a resolver and the authoritative name servers. A resolver is a caching service that will go out and do the work and to find the address and communicate with the authoritative name servers, but they don't hold the source of truth. The source of truth is in the authoritative name servers, of which there is a hierarchy, but yeah, just calling out that there's a difference. When you look at like Cloudflare DNS or Google DNS, like which is like Quad 1 or 8888, those are resolvers, public resolvers. So the authoritative name servers are organized in a hierarchy where there's delegation to different areas of the domain name system. So at the very top, we have the root. And the root will delegate to other name servers and not actually answer anything itself. The only thing that the root name servers do is they point to a few other name servers, like the .com name servers. So anything that's under .com, it'll point you there. And then even the .com name servers, they don't have all the information for all the records. They will delegate to another level, like the example.com name servers. And so if you actually want to get an answer to your query, you have to go another level, and they'll have the real answer. So this is another depiction of that. So at the top we have the root, and this might be the .com, and it points to example.com, and so these are different zones. And again, the higher levels just delegate and provide pointers to lower levels on the hierarchy. So what actually happens? Your browser, say you want to go to example.com, your browser looks in its cache. Okay, it's not in the cache, and it goes to it makes the system call getAtterInfo, and your operating system will communicate to the resolver. And the resolver looks, and it's like, oh no, I don't have that in my cache, so I'm going to have to figure out the answer from scratch. So I'm going to go talk to the authoritative name servers. So we'll go to the root name server over here, the triple crown, and we'll say, what's the IP of example.com? And it's like, I don't know, but I can point you at the .com name server, and it's here, it's orange. And then we start a new request, and we say, what's the IP for example.com for the .com name servers? And it's like, I don't know, but you should ask the blue example.com name server. And we go to the blue name server and we say, what's the IP for example.com? And it's like, here it is, 93. Blah blah. And the resolver's like, okay, great, I will send that back to the browser, and then the browser will actually be able to communicate. This is another depiction of just what's happening here. User communicates with a recursive resolver, it goes out to the different name servers, and then the response comes back. So this whole system is bootstrapped at the root. And the root name servers are described in what's called the root hints file. And this is the actual beginning of the file. There are 13 addresses, A through M. And so each one has a v4 address and a quad A record, quad A address. And so this is it. This has been the A name server, or the A root record, for a long time, and it's going to stay that way for a long time. This is actually how this entire system of gigabytes, hundreds of gigabytes of data is bootstrapped. With this information, you can go through and ask little questions and get all the data.
So A root would be like all the examples start with A.
No, it's not like that. It's just they are all the root name servers, and they all have the pointers to like the TLDs, .com and stuff. They were just like, we need a number of them, and I think there's some reason that there's 13. There's like some limitation built into the protocol or something like that. And so let's just name them all. Let's name them A through M. But yeah, there's they all have all the same data. So dig is a command line tool that you can use to examine DNS records. And you just do dig example.com, it comes back, this is the name that you search for. The TTL is one of the most important aspects of DNS. So, and it is where things usually go wrong. So DNS is an eventually consistent database. Records are cached in many, many, many places until the TTL expires. And there is nothing that you can do to remove it from cache. And so, if you update if this is your record, and you update this to the wrong value, and it goes out and it stays in cache, it's there for a day. There's nothing you can do about it. And so, sometimes when making, sometimes this is how errors happen in adjusting DNS records, and then it's very hard to recover from. And so a good strategy, if you're editing DNS records, is to reduce this TTL. So if I have this record and I reduce it down to 30 seconds, this is a good start. But that record is already out there with a 1-day cache time. And you have to keep that in mind. Even if you change the TTL, it's still out there. And nothing is changing that. And so if you change this to something like 30 seconds, then you need to wait the old TTL before you make changes. So you reduce this to 30 seconds, and then you would wait a day. Now, after that day has passed, you have confidence that if you change this value, then all the downstream services will pick it up within 30 seconds. And if you mess it up, then you have the ability to change it back. And so it might be surprising that DNS is like really simple and it's like basically UDP request, and there's no authentication, there's no encryption for most of DNS. And that's really surprising considering how important DNS is. Like, I want to know when I go to mybank.com that I'm actually going to my bank. I'm not getting the wrong DNS record that would point me to some nefarious website. And so it's a little bit surprising that we've managed to get this far without adding a lot of security to DNS. And it's true that ISPs can examine DNS queries and responses and even inject some falsely reply to them. So like this is what some ISPs will do. If you type in a bad domain name, it will change the DNS response and it'll redirect you to a website that then displays ads. They're like, we want some of that Google money. There are some efforts to increase the security of DNS. We're running out of time, so I'm going to leave those for reading in the PDF that you'll receive. But I hope you check it out. I also talk about how the root name servers are Anycast DNS and some confusing things with how those resources can be geographically distributed but use the same IP address. So that is networking. But I wanted to take I have a few parting words to dispense while I have your attention. So you'll find that when you enter the workforce, it's really easy to get on this, what I'll call like a consumerist hamster wheel. You buy like the new computer, you get a new car, work really hard, you get the promotion, you climb the corporate ladder. You get a mortgage and move into a nicer place. And suddenly you're kind of trapped where you need to keep your job and you have no opportunity to explore other options, and you end up like working a job that you hate just to pay the bills.
Are you scared?
Well, I bring this up because I urge you to consider thinking about like a more sustainable path to happiness, which is a positive impact on the world. I know that you're all very intelligent just because you're here in this room with me. And I want you to use that intelligence and drive to improve the world. There's so many things that you can do. You can volunteer, you can donate, you can teach. Maybe you care a lot about AI and you want to get a job at a big tech company so that you can shape it for good. Great. Spend some time thinking about what you consider to be really important and how you can use your skills to improve the world. One path is to spend your career working on important problems. this organization, you'll spend about 80,000 hours in your career, which is a lot of time. And that's the name of a nonprofit organization that encourages people to spend their career in an impactful way. They have really great resources at 80,000hours.org about how you can do good I really like their resources. Another option that doesn't require you to do any particular kind of work is donations. With an average software engineering salary, if you donate 10% to like the right efforts, this is a strategy called earning to give, you can save over 40 lives over your lifetime. That's incredible. So I listed off some of the accomplishments that I've had at the beginning. It might surprise you to hear that I lost like years of my life to soul-crushing depression. Like, I didn't work for 4.5 years. Lots of therapy, lots of medication. It was by far the toughest time of my life. And I'm now like infinitely better, and there were many things that helped me, but making service to others part of that was definitely one of them. So that's all I have for you guys. Thank you guys so much for listening. I'll stick around for a little bit. Happy to chat about anything. And yeah, thank you guys.